Vector equations and spans. And span is something that's very important. I'm going to put a little asterisk here. You'll see it for the rest of our class. And sometimes it may take a while to really understand what spans are. So I want you to pay very close attention and make sure you can explain spans to yourself after this lecture. All right, let's start with a definition. All right, so we are going to let V1, V2, all the way to VP be elements of Rn. So all P of these vectors have n rows, so they're in Rn. And we say that the span of that set, so V1, V2, all the way to VP, can be given by any vector u that is also in Rn, such that u equals C1V1 plus C2V2 all the way to plus CPVP. All right, so this is what we call a spanning set or a span. So the span of all of these vectors is any vector that can be written as a linear combination of these. And so you may also see the span of a set of vectors called the subset of Rn generated by those vectors. All right, so we can get this subset by finding linear combinations of these vectors. All right, so another way that we can think of this definition another way to say this would be to say the span is the set of vectors in Rn that can be written, that's an E, all right, let me turn my notifications off my computer. All right, so the span is a set of vectors in Rn that can be written as a linear combination of those vectors and still be in Rn. All right, so both of these statements mean the same thing. It's the set of vectors, so this set of vectors in Rn that can be written as a linear combination. All right, so let's look at some examples. All right, first example, let's look at this vector in R3, -7, 4, 0. All right, and I say that this vector is an element of the span of these two vectors, 1, 2, 3, and 3, 0, 2. All right, and how do I know this? Well, it's an element of the span because we can take our original vector, -7, 4, 0, and write it as a linear combination of these two. So we should get -7, 4, 0 by multiplying 2 times 1, 2, 3, and then subtracting 3 times the other one, 3, 0, 2. All right, and so When you multiply across each row here, so you'll get 2 minus 9, that's negative 7. 4 minus 0, that's 4. And then 6 minus 6 is 0. So that means that this vector is in the span of these two because it can be written as a linear combination of those two. All right, let's look at another example. Okay, let's take the vector in R2, 1, 5. All right, and I say that this vector is in the span of 2, 3 and negative 1, 2. Notice that these are in the same space, so they have the same dimensions. These are all in R2, these are all in R3. That should be the case all the time. All right, so I say it's in the span because I can rewrite 1, 5 as a linear combination of these others. I can just add them together. So 1 times the first one plus 1 times the second one. Let's look at another example. 2, 3. All right, so I'm saying it's in the span of 2, 3, negative 1, 2. All right, so notice one of the vectors that I'm saying 2, 3 is in the span of this set is also 2, 3. Of course, 2, 3 is going to be in the span of itself. Of course, you can write 2, 3 as a linear combination of itself, but what about this piece? Well, we can multiply by 0. That's fine. Okay, so we can write 2, 3 as 1 times 2, 3 plus 0 times negative 1, 2. All right, and notice these two vectors are in the same spanning set, and that is okay too. All right, next let's look at another example, do a little work for this one. So the question is 2, 1, 3 in the span of 1, 2, 3, 3, 0, 2. Most of the time, we won't be able to just look at these and figure out the answer. So of course, there's got to be a step-by-step method that we can follow all the time to let us know if a vector is in the span of a set. And that method is row reduction. So we can set up an augmented matrix because really we're just trying to see, can we solve something times this one plus something times this one equals this one? This is the linear combination we want to solve. Or the linear system we want to solve. So we can set up our augmented matrix, right? We got 1, 2, 3, 3, 0, 2, and we're going to set it equal to 2, 1, 3 because we want to find what scalars, x1 and x2, to multiply by these vectors to get this one. All right, so I am going to row reduce this, and then I'll let you row reduce this as well, and then in the next video we'll talk about the solution.